Hello, everyone. I'm very happy to see you all here today. Thank you for coming. I'm Lena. I work as a software architect. I am interested in distributed cloud programming, data science, and machine learning. I'm also a member of F# Software Foundation Board of Trustees, so if you have any questions regarding F#, feel free to reach out. That's about me. What about you? I assume that every person in this room has some basic understanding of what machine learning is. That's right? Okay, but I'm curious how many people from here have actually applied some machine learning techniques on their own projects. Raise your hands. Wow, that's cool. Okay. So, why am I doing a talk on machine learning? Machine learning is not something from the faraway future already. It's here now. So, if you haven't done any machine learning yet, there is a very significant probability that you'd have to face with machine learning tomorrow in your daily job. And why? Because machine learning can be applied to any areas and domains. They all have data, and you can always learn something from data. So, is it easy? Well, machine learning is not obviously a very easy task because it requires at least basic understanding of what's happening under the hood. But it's not so hard either because there is a lot of frameworks and tools that you can apply to do machine learning on your own tasks if you don't want to implement it from scratch. So, for example, there is Accord.net, and you'll see today how we can apply it with F#. So, in this talk, I will walk you through some amazingly interesting machine learning things we can do in .NET just now. And I will be mostly focusing on F# because F# and functional programming in general is very suitable for machine learning tasks and tasks that, for example, data processing tasks that precede machine learning problems. So, what is machine learning? When we have data, we want to get the largest amount of useful information from this data. And if we have data and we don't know anything about this data, we still may want or intend to find out something from it, to identify the information, and to learn something from it. And we still can do it with unsupervised machine learning. So when you're very new to machine learning and don't have some specific mathematical background, it may seem a bit unclear at first glance when you see all the variety of existing algorithms and approaches and techniques that you can use. But as you go deeper and deeper, you start to understand the structure of machine learning. By structure, I mean approaches and algorithms and differences between them. When we have our usual programs, we usually have an algorithm and step-by-step instructions that give us some output at the end. Machine learning program goes a bit differently. There is data, there is machine learning algorithm that uses this data to gain experience. It learns from experience and uses this experience to produce more accurate results in the future. So when you decide to dive into machine learning, you'd have to go through the checklist of 3 important questions. Why, what, and how. So the reason why you actually need machine learning is very important. You should be able to answer this question for yourself. There are a lot of areas where you can apply it. For example, recommendation systems, text recognition, for example, for spam detection, recognition of unspecified items, some audio and video analysis, classification, and other areas. In addition to areas, there are spheres or domains where you can apply it, like biology, science, medicine, media, finance, so whatever domains can use machine learning. And the next thing you'll face is data. So what is your data? With machine learning, you can use any kind of data. And almost in all cases, data needs pre-processing. In vast majority of scenarios, you'd have to do something with your data to be able to effectively learn from it. So I decided to ask a question to find out how clean data would be that I get to as an answer on my strictly schema question. So I asked on Twitter to tweet the favorite musical genre, then comma, and then most favorite programming language with the hashtag. Several hundred people responded to this tweet, and instead of helping me to dive into my machine learning adventure with perfectly structured data, as you see, some people intentionally answered like wrong. They decided to broke my parser. Yeah. Some people even were polite and said sorry about that. Some people just wrote that all programming languages sucks, and this tweet got most retweets and favorites. And even Michal participated with his optimistic every and any option response. So this is very, very true. In reality, you'll never get perfect data. You'll always need to do something with it. And some data scientists say that before actually starting their machine learning tasks, they have to spend 70% of their time to do data preparation. Well, and the last question is how to actually learn. This is a picture that I found over the internet, and I like this picture a lot. It's not mine. The author is Swami. You can find him. He's doing some data science work. And this is like a map how you learn machine learning. There is a number of some algorithms. So the basic idea is to understand what we have and the differences between algorithms, so we'll be able to do an effective choice. That's what we'll do right now. I will try to walk you through some examples, what we can do in .NET and F# with Acquire.NET. I will show you 4 examples, 1 on regression, 2 on classification, and 1 on clustering if we have time. I intentionally chose fairly simple examples, so you'll be able to focus on the actual algorithms instead of the diving into example domain. This topic might be advanced for regular software engineers, but for machine learning people, it would be the very foundations. So let's start. We'll be using Acquire.NET framework and F# for doing machine learning and data science. The first algorithm is linear regression. So this is the simplest algorithm in machine learning that we can use ever. Suppose we want to predict something. Let it be exchange rate for some day in the future. And regression is the prediction of some number from the continuous range. In supervised machine learning, we always have the trained data and test data. Trained data is when we have our inputs and outputs are already known. Test data has only inputs. So inputs here can be, for example, some political or financial situation or conditions. It can be weekday, workday, holiday, or some other things. The idea of linear regression is to find a function that will fit the training samples in the most optimal way, as you see on the picture. Here, imagine that each training sample represents the point on the picture. So the idea is to draw the line that would fit all points in the best way. Anyway, let's look how this linear regression works and dive into some math. So how can we even predict something? Well, it's rather simple. We can just make a guess. We can then find out what is the mistake, so how wrong we are, and after that fix our mistake. So the first step is to make a guess. The simplest case of linear regression is when we have only one input parameter and one output parameter. So as if we were to predict the exchange rate, knowing only financial conditions on the market. And then we can locate all our training samples in 2D space, 2D picture, to make a guess. That means that we are trying to draw the line that should ideally fit our data, but as it's the guess, it's obviously wrong initially. That's why the line doesn't fit the data at all. What does it actually mean to make the guess? Guess is what we are making in the simplest case. It's just a line. As you know from the high school, line can be represented as the function ax plus b. So we can draw it through 2 points. So to draw the random guess, we'll just randomly select 2 points and draw the line through it. So if we have the more complex guess, we'll have n parameters, n input parameters, and we'd have to select n random points to draw the line through it to make the fit. These theta parameters in the function are also called weights. Now we have our training data, we have our guess, what we've made, and now the goal is to measure how wrong we are. What is our mistake? How can we do it? We can define the so-called cost function or mistake function. So we can do it because we have training data, and for training data we have actual outputs. So we will just send our input parameters x's to our guess function or hypothesis function and compare the result that is produced by the guess function with the actual result. And this is what our cost or mistake function is doing. It uses the squared error function to find the difference between the actual output and our guess output to find out the mistake. So it just sums the values. So what this mistake function basically means, what it gives us. It shows how wrong our randomly selected theta parameters or weights are. So what we're going to do with this mistake, we want to reduce it. We want to get rid of mistake. So to do it, we can just minimize the function. To imagine this cost function, it can look like this or like this or like this. So when our initial guess is made, that means that we are located on some random point in this shape. And to reduce the mistake, we need to go through, to go from where we are to the minimum of the function, to the place where the mistake is the minimum. So we'll get the most correct values for our theta parameters, for our weights. But how do we know where the minimum is? We can know where the minimum is if we count the derivative of the cost function. Derivative can be either positive or negative. If it is positive, that means that in the point where we are, it looks like this, and the minimum is located on the left. And if it's negative, it looks like this, and the minimum is located on the right. So it defines the direction where we will go from our point. But direction is not enough. We actually need to make steps. To make steps, we should define the size of the step that we're going to make from the point towards the minimum. And the step is defined through the learning rate. Learning rate, just a number, that we are making our steps. So basically what we're doing, how are we moving? We are updating each of our data parameters simultaneously, and we are updating them. We're moving in the direction of the minimum. The direction is the derivative. So we're moving left if derivative is positive, we're moving right if it's negative. And the learning rate is this alpha parameter. It's the size of our step. So we're doing it until we reach the minimum. But how do we know if we reach the minimum? The derivative in the minimum will be just very close to 0 or 0. So after we minimize the cost function, we'll know the correct values for all our theta parameters. So we will be able to just draw the correct line through all our training samples. That was the simplest case of linear regression. Linear regression when we have only one input and one output. But now let's look into some example where we have several predictors, several features, and output. So let's say we want to predict the demand on bike rentals on some day in the future. We have some statistical data about the bikes, and we want to guess how many of them will be rented someday in the future. So it is more complicated than a line. It can be 2 or more dimensional, like a data dimensional. And when our guess is correct, our shape will be optimally fit the data. So let's look into some F# code. So here is a sample. First, we're importing some libraries. We are using Accord.net, so we import all the frameworks. We are using Accord models, regression, linear, and fitting. We have predictors, so how our data looks like. Our data looks like this. It is a CSV file with some parameters about the situation, like season, year, month, holiday, weekday, working day, weather situation, temperature, humidity, and other things. And we'll use it here. We're not using all the parameters, we're using some of them. And we have some type that is called bike data. It is represented as predictors and outputs, so they are all floats here. What we're doing is getting bike data. We're using CSV files to do this. We have a function called bike data. The first line, we just load the file that's called bike sharing dataset day. And then we spread it to predictors and outputs and just return it into F#. Then we have a function that is called bike demand. What we're doing is getting data. And then there is a special class in Accord.net called multivariate linear regression. It takes inputs and outputs. We know that we have 13 predictions and 1 output. 13 predictions is this array predictors, and 1 is what we want to predict. We want to predict the demand on bike rentals. So we want to, and then we want to do regression on this. This function is very important because it does everything that I've just told. It sets all the theta parameters randomly. Then it finds the cost function. It minimizes the error and gives you the correct prediction. Let's say we have season. Season is special format like 1, 2, 3. It's fall. It's 2015. It's September. It's not holiday. So all these parameters. Let's define them and find out what would be the amount of bike rentals. To do this, we're using regression.compute, and it gives us the result. So this would be the value. If we want to know the actual theta parameters, that were, if you're curious, you can do this. We have 13 of them, and you can find out their values. That's it. So this is how multivariate linear regression works in F# and Accord.NET. Let's switch back to the presentation. So that was the simplest machine learning algorithm, and it's very fast and runs in constant time. You can use many features with this algorithm. It's good for numerical data, so you can use it with Accord.NET and F# very easily if you don't want to implement it from scratch. The next thing is logistic regression. It's not this name is somehow confusing because it's not regression, it's a classification algorithm. It means that output is not just a number from some continuous range. It is a category like black or white, yes or no. So logistic regression is the classification algorithm that can have two categories of the output. So it's like binary classification algorithm. Here we also have our guess function or hypothesis function, but it is a bit different. If in linear regression we had a line that we wanted to build as our guess, here it is the probability that output would be 1 for some given set of predictors. So here we also do some random selections. So this is theta, the set of randomly selected theta parameters or weights for the given input set. And the difference is that in this formula, this is a sigmoid function or logistics function. It outputs the value from 0 to 1. And there is also some threshold or value like 0.5, and if the value would be more than this value, it would be closer to the first category, or if not, it will be closer to the second category. So here all the same, we're making a guess, so we're randomly selecting the values for the array of theta parameters. But this guess will look like this. Then we have the mistake function. It looks a bit differently too, because we have two outputs. We have two configurations. Output can be either 1 or 0. So if actual output is 1 for the given data sample, and if our guess is 0, which is wrong, then the value for the mistake should be increasing as our guess decreases. This is the blue line. If our actual output is 0, and if our guess is 1, which is wrong, then our mistake should increase as our guess increases. This is the green line. So that was the mistake function for one data sample, and this is the mistake function for all data samples. It's just a sum. Don't be scared of this formula. So it uses the principle of maximum likelihood estimation and based on probability. And to minimize this function, we use the same approach that with linear regression. We just find the cost of it and move towards the minimum, minimize it the same way. And let's move to the example. So here we have logistic regression. Once again, yeah. Yeah, this is the problem. So I'll move a bit back to the presentation. So here, as you see, some shapes can have several minimums. So for example, on the lowest shape, there is some global minimum and set of local minimums. So to prevent, for example, if we are making the guess that is wrong, but the guess can be closer, for example, to this minimum, which is not the global minimum, it will find the local minimum, so it will be not quite correct guess, and we'll be stuck there. But to do this, we'll need just to do it once again with other random samples, to maybe with different learning rate, so the number that indicates steps, and then we'll be in another point, and we'll be finding another minimum. So this is all like experimentation and iterative process. So with our logistic regression, we're also importing the libraries. And here the example is the following. We have two predictors. One predictor is the person's age, and the second predictor is whether the person smokes or not. So what we want to do is to find out, to know if there is any connection of smoking and lung cancer. So we have also number of output sets that indicates if the person have ever had lung cancer. What we are doing is initializing our inputs array, our outputs. So 0 means that the person had not had the cancer, and 1 means that it had. And regression, that is the instance of logistic regression class, and we are defining it with number of inputs. What we're doing here is finding the distance. We're going to estimate the model, and we're finding the distance between our guess and the actual output. And this lines is the actual teaching process. We do teaching until we're close enough to the minimum. And there is the parameter that indicates how close you want to be to the minimum. You do teaching. And here, to find out the result, to know the prediction, you just use the regression.compute to make this. So it outputs, by default, it outputs the probability of that y would be 1. So the probability that this person, that age is 56, that smokes, will have the cancer. It's all fictional data, so just as an example. That is, as for logistic regression, what need to remember, this is classification algorithm. The output is binary. It's good when number of predictors is relatively small. It uses logistics or sigmoid function for guess function. It also uses cost function and the algorithm that minimizes our cost function, which is called gradient descent. At this point, it may seem that what society thinks that machine learning is, what other programmers think I do. Yeah, so let's move next. Neural networks. Neural networks is extremely powerful algorithm for both classification, regression, and other things, but we'll use it here for classification. It is the way to simulate the neurons, the brain neurons, for programming and for machine learning. It is good for a big number of predictors, and the largest neural network in the world is right now in the Stanford University. It has more than 10 billion predictors. So let's look what it is. So I think you know that neuron is this thing. It has dendrites. That's some things that we can receive input from. There is the axons, the way we can produce the output from the neuron. and there is a core where all the computation is done. So the neurons can be related, can be connected, and axons can receive dendrites can receive inputs from the output of other axons. So what about programming? Here it is represented this way. So we also have a set of predictors, here inputs. We had a number of outputs, and we have a number of hidden units. So we have 3 layers. 1 layer for getting the inputs, 1 layer for doing computations, and 1 layer for getting the real outputs. Here we can imagine that this is our X set. And to make a guess, we also need to actually assign weights for each of the predictors. We'll see it later. So what's happening here? Why do we need hidden layer? It is created for doing the mapping from input to make the output from it. So how are we making a guess? We need to somehow convert input to the correct output. It sounds kind of strange, but we're doing the transformation from inputs by the summation of theta guess parameters to find out the values for each of the hidden layer neurons, and later transform into the output. So it can look this way. For each neuron in the hidden layer, we do the following. We take the input, we take the weights that we randomly select. So here we are randomly selecting weights for each hidden neuron. So if we have 4 hidden neurons and 3 inputs, we'll have 3 weights for the first hidden neuron, we'll have 3 for the second, and so on. So we'll have like 12 of them. And then what we're doing, we are finding the product of these sets and sending them to the activation function. You can now think of the activation function as some function that produces the value for the hidden neuron. It takes the input, takes the guess parameters, and produces the value. What is actually the activation function? It is kind of similar to, it is the classification, so it will be a little bit similar to the logistic regression. If we have only 2 options for the output, either 1 or 0, we can use step activation function. It is used in binary classification. So that means that if some value is greater than some threshold value, it will be 1. If not, it will be 0. Or we can use some probability-based function. So it is the same as in the logistic regression. It is called activation function because it produces the value for the hidden layer neurons. So if we look to the whole picture, what's happening? Here you can see the predictors, the inputs. You can see the hidden neurons. As you see, there can be multiple layers of hidden neurons, and you can think of arrows as theta parameters or weights for the neurons. So the first step will be finding out the values for the first layer neurons. What we do is sending the inputs to the activation function from the first layer and finding out the results for the hidden neurons in the second layer. When the values are ready, we're doing the same, but with the next layer. We're forgetting completely about this. We're excluding this. We're thinking of this activation neurons of the hidden layer as predictors for this layer. So here we can think of X's as for the second layer neurons of the hidden layer. And finally, when there are no layers of the hidden neurons more, we can find out the actual results. So For example, if we have used a step function, there might be 3 configurations of the output. So we can say that if there is the first category, the first neuron will work. It will be 1. If there is if the second neuron worked, there will be the second category, and so on. If we have used the probability function, we would have to find the maximum value from the array to find out what value worked. So the cost function is very similar to the linear regression cost function, but it just adds the neuron layers, and that's it. It's not very difficult. It's very similar, and later we'll find out the mistake and minimize it. So for neural networks, it's a bit differently. So how can we find out the mistake if we can actually find out the mistake only for the output? Because we have training samples, and we can compare the output and the guess. So we can find out the mistake on this layer by just distracting the values. But how can we find out the mistake for the hidden layer neurons? There is a way, and it uses this formula. So as we're setting the guess parameters, we are multiplying our guess weights and the mistake from the previous layer. So simple words, it works this way, and it goes back and back until we reach the input parameters where the mistake is 0, because this is our input parameters. And finally, we'll know what is mistake for each of the theta values or weights we set before. And then we'll be able to recalculate it. So let's look at some example with it. And in neural networks, it's not always necessary to actually know the data. It's the way we can use it with some unknown data where we can learn something from it. So in this example, I have the wine data set. Sure, I'm expert in wine, so I selected this data set. It looks like this. We have training and testing. So we have class, alcohol, something else, some parameters that are valuable to determine the class of wine. And we have 3 classes of wine. The first value here means the class. So what we want to do now is to import this. These are functions for normalization the data. Normalization is important because it's much easier to work with data that fits the same range. So I'll tell about it a bit later. Predicted class. How are we getting the data? We have the function that is called getWineData. It receives the pass. What we're doing inside, we are getting the file from the csv_file.load, and we have columns that we want to use to our machine learning. What we're doing is finding the input data. So input data is just columns for predictors. We're skipping the first column because we don't need class. We want to guess the class. For normalization, we also need minimums and maximums to be able to use it. There is a method that checks how right we are in our machine learning, and all interesting things start here. So I'll expand it a bit. Here we're getting our input classes, outputs, minimums, and maximums. I will tell you what's it. So here you see the data that we got from the file, and all classes separately. We'll need it to compare later how wrong we are. Here we're using the sigmoid function. The sigmoid function is not the binary function, just a function based on the probability. And we're creating the network, activation network, consisting of 13 input parameters, 3 output parameters, as we have 3 classes, and let's say 79 hidden neurons. So the number of hidden neurons is the number that you should experiment with. So you'd have to find the number that will ideally fit for your computations. So there is no special way to say what number of hidden neurons you should use. You should try. Let's initialize the activation network, and this line randomly initialize the network, so it finds out the random weights for each predictors and each hidden neuron. So we're using parallel resilient backpropagation learning class and passing the network to it. This class basically does the algorithm that will find out our guess, that we're doing the transformation between inputs. We're doing the transformation from inputs to the hidden layer neurons and from them to the guess outputs. And then we are teaching our neural network. This is the function and actually the process. And after that, we will be able to check the accuracy. So as you see, there are some correct and some incorrect parameters, but it's not bad result. It's very important to pass the correct data to some algorithm that you're doing machine learning, because surely sometimes you'll have data from different ranges. So some of your predictors can be from -5 to say 200. Some of them could be some float values ranging from 0 to 1, and it's very nice to normalize your data before actually using it. So normalization means that we are somehow making the range for our predictions the same. So all of our data will be from 0 to 1, for example. So this is how neural networks work with Acquire.net. Let's move next. So this is extremely powerful algorithm. It is very good for predictions. Sometimes it can be slow for learning, but you can always distribute it, for example, with using Embrace and clouds for running your machine learning algorithms. And the last algorithm I want to explain is K-means. K-means is the type of unsupervised machine learning. It is used for clustering. So you don't have training data or testing data. You have just data, and you want to somehow group it and to find out something from it, to notice something from the group data. So let's say you have data that look like this, and it finds how the data is grouped. So you'll be able to find the relations between it. And now, so this is an example. Here we have the file. It's called birth death rates dataset, and we have some data in it. It has countries and the percentage of birth rate and death rate for these countries. So we want to notice something about it, and we are using this file in F# Visual Studio to find out the overall picture. So the first thing is usually importing libraries, getting the data. So it's very simple for this example, because we have just 3 parameters like country, birth rate, and death rate. We skip the first just because we don't need it now, and we want to find clusters. We want to find the relation. We get our input data. Here it is. And let's say the algorithm is called k-means. So k is a parameter. It means how many clusters you want to notice. Let's say 2. And then we are indicating the mistake that we want to use with our algorithm. The less mistake is, the more correct machine learning process will be, but you can also experiment with it as usual. So after that, after we have inputs, we are sending them to k-means.compute. And what it does is produces the labels that it thinks data corresponds to. So it grouped it into 2 categories. But it's not very convenient to look at it this way. It may be more convenient to just display it somehow. Here it is. So it grouped our data into 2 categories. You can see that for some countries it's really on the bottom, and for some countries it's going on the top. So there you can be later doing some relations from this data. We can also increase the number of clusters. So we can indicate 3 here, for example, and when we want to group it into just 3 clusters. And then also compute once again. Here you can see that if previously we had only 1 and 0, now we have 2, 1, and 0. And now it should be displayed with 3 clusters. Like here. So that is about clustering algorithm. And you can use it if you are not really sure what exactly you should find out about the data, if you want just to group it somehow. So what's next? Next, machine learning is really a huge topic, and you can select any kind of algorithm, and for any kind of task you just need to be accurate and understand differences between them. And you can always use tools that do this for you if you don't want to implement it from scratch. But still, it's very nice to have the understanding of what's going on under the hood. So you'll get the presentation, so you'll get this picture. I'm Lena. It was very nice to speak for you, and thank you.